All right, welcome back to another session of Introduction to Photonics. So, what we have been discussing lately is light generation and amplification. We have been specifically looking at how photons interact with matter, through which you could have absorption of those photons, and subsequently you could have emission of photons either as spontaneous emission or stimulated emission. And we took this example of an optical amplifier which is part of an optical fiber communication system. So, as we know now, erbium doped silica fibers are used in these optical amplifiers, and erbium doped silica essentially consists of 3 energy levels. So, you are able to go from the ground state, the valence orbital of this atom, erbium atom, to a higher energy level with the absorption of 980 nanometer photon. And then we said the excited state is relatively short lived. So, and then the next energy level is relatively close. When I say relatively close, what I mean by that is that energy difference is corresponding to the phonon energy of the glass. Okay. Phonon energy is the vibrational energy that you have in the glass. So, when you have two energy levels that are very close to each other, that is within the phonon energy of the glass, you lose that energy through just non-radiative relaxation. Okay. So, that is what is happening in erbium. It goes to that higher energy level and then goes down to one step below, where that energy level is relatively long lived. So, this energy level is in the order of it has got a lifetime the order of 10 millisecond. So, whatever you pump to the higher energy level goes and stays or accumulates in this higher in this particular energy level, which has 10 millisecond lifetime, and through that, through enough pumping, you create population inversion, and once you have population inversion, you have the stimulated emission happening, wherein a weak photon at or a weak radiation consists of a few number of photons at 1550 nanometer, goes through this amplifier and gets amplified into a much larger number of photons. So, we had been looking at an expression for this inversion as a function of the pumping rate, and we got to that expression in the last lecture. But before we go to that, I want to make just one point about this. So, remember we were looking at this erbium absorption spectrum, erbium in this other glass, which is bismuth based glass. We said this was the absorption spectrum. One quick point to note as far as this is concerned is that this absorption spectrum corresponds to essentially absorption between different energy levels. So, I can basically say that my ground state is somewhere over here. I have some excited states over here, another bunch of energy levels over here, another bunch over here, another bunch over here, and so on. Okay. So, what we are doing here, if you were to visualize this, is you are going up in energy, right. So, whenever you see an absorption spectrum like this, you can say that your ground level is the lowest energy level is on the rightmost side, right, and from there you are making these transitions to the higher energy level. So, each of these absorption peaks correspond to one of those transitions. Do you understand what I am saying? Is there a question on this? Right. So, this is one way of visualizing the absorption spectrum of any given element. Okay. But we were considering erbium as a 3-level system, wherein we are pumping into this energy level, we do a non-radiative relaxation to this this band of energy levels, and from there we are having stimulated emission when this transition happens. Okay. So, that is what we are talking about. We just turned around the energy level energy band diagram when we were considering this in the previous lectures. Okay. So, we stopped at the point where we looked at the inversion that you could create for a 3-level system, and erbium in silica is actually a good example of this. And the inversion we said is equal to n naught over 1 plus tau s w I, where n naught, what does that correspond to? That is the inversion that you get when there is 0 photons, 0 signal photons that are coming through, right. So, to get this inversion, obviously you are pumping this system, right. So, you are supplying pump photons to take these erbium ions from the ground state to an excited state, right. But assuming you do not have any signal photons coming through, you would be maintaining a certain inversion, right. That inversion is what we call as n naught. And then tau s, we got a expression for that. Tau s corresponds to twice the spontaneous emission lifetime, that is the lifetime of your excited energy level or N2 energy level with corresponding number density N2, and then we got an expression for n naught as well, right. So, we stopped at this point where we derived an expression for n naught, which depends on r, where r is what? What does r correspond to? The rate at which we are pumping, right. So, the pump photons which are taking the erbium atom from a ground state to an excited state, and Na, what does Na correspond to? So, that is the total number density of erbium atoms in this in that fiber, in the gain medium, right. And one thing I did not mention explicitly is Wi. Wi corresponds to the rate at which the stimulated emission or the stimulated absorption happens, and Wi corresponds to the flux density multiplied by the cross section, whether it is the emission or absorption cross section. Okay. Now, where we stopped is what this graph is showing us is as we increase. So, initially when we have 0 photons coming in, signal photons coming in. So, this flux density is corresponding to 0. You have a certain inversion for a given pump rate, and then as you increase the signal photon flux density, right, as more and more signal photons come through, we see that the inversion that is available to you is not as much as in the case of 0 signal photons. So, the inversion decreases, and there is one particular point at which the inversion becomes half of what it was when there was no signal photons. That is what we are denoting by n naught over 2, and the corresponding rate is given by 1 over tau s. Okay. So, this corresponds to certain characteristic rate, right, and the time corresponds to some characteristic time, which we will come back and define as the saturation lifetime of this system. Okay. And what happens as you go to higher and higher values of flux density, signal flux density, is that your stimulated absorption and stimulated emission terms dominate. So, essentially they have equal probability, right. So, the stimulated emission and the stimulated absorption typically have equal probability, in which case the gain essentially goes to 0. Okay. So, when Wi is very large value, what we are seeing is that the gain actually goes down to 0. Okay. So, let us take an example. Well, we will continue with the same example of erbium silica gain medium, but let us start quantifying a few things. So, let us just work out an example problem, right. For erbium, it is given that the spontaneous lifetime TSP is 10 millisecond, and you are asked to consider the total number of the total number density of erbium in this medium as 1 10 to the power of 24 per meter cube, right. You are asked to figure out what is the minimum pump power density required to achieve inversion. So, inversion essentially means that your n2 minus n1 is greater than 0, or n is greater than 0, right. So, what is the minimum pump power density required to achieve inversion, and you are also asked to figure out what is the saturation flux density. Okay. Suppose you are asked to figure out these two quantities, the saturation flux density you would denote as phi sat, right. So, what is that value is what's asked. Okay. So, what we know is this, that your inversion is given by n naught over 1 plus tau s Wi, where n naught is given by 2 times R TSP minus Na. Okay. So, the minimum pump power that you need to achieve inversion, that is n naught is greater than equal to greater than 0, right. So, to do that, to achieve that, what condition do you have to satisfy? So, let us say this is A and this is the B part. In the A part, what we are saying is that you have a 2 times R TSP minus NA has to be greater than 0, right. So, for N naught to be greater than 0, that is the condition. Yeah. So, your pump rate, the minimum pump rate has to be equal to NA over 2 times TSP, right. So, that is the minimum pump rate that you require to achieve inversion. And at this point, it is probably helpful to understand how the inversion changes or how the inversion depends on the pump rate, right. So, if you were to plot the inversion n as a function of the pumping rate, how is that going to look? Let us say we are specifically looking at N naught as a function of the pump rate. What sort of dependence is that? That is a linear dependence, right. So, you are basically going to have a linear dependence like this, and what that tells you is for small values of R you have negative inversion. What does negative inversion mean? More ions sitting in the ground state compared to the excited state, and then you get to a certain value of R where that inversion is equal to 0, which means there is equal number of excited atoms to the ground state atoms, and that value is now given by Na over 2 times TSP, right. And then beyond that you have higher inversion that you can build with higher pump rate, and that does not extend forever. It will saturate at a certain point. Why does it saturate? What does it happen? What is happening beyond a certain pump rate? No more ions on the ground state. So, you have a finite number of these erbium atoms in the matrix, and if you flood the gain medium with so many pump photons that all the erbium atoms are going to the excited state, there is no more erbium atom in the ground state, right. So, there is no more inversion that could be created, right. So, this is basically due to what is called ground state depletion, right. So, every gain medium you can say is going to have a finite number of these atoms, and beyond a certain pump power level you are going to deplete the ground state, and you are going to saturate the inversion, and because your inversion is saturated, your gain is also going to get saturated. Now, this saturation that we are talking about is different from the other saturation we discussed previously, right. The other saturation here, what is this due to? Here when we talk about grain saturation, what are we talking about? We are basically saying that the gain is reduced as you increase what? Input signal flux density. So, it is all with respect to the signal photons. As you increase the more and more number of signal photons, your gain is reducing, right, because as you have more signal photons, more stimulated emission happens, which takes away the inversion, which reduces the inversion. Okay. So, that is, this gain saturation is due to signal, whereas this gain saturation is due to the pump, right. So, as you go to a very high level of pumping, you start having saturation of the gain, and that is due to ground state depletion. You see the difference between the two cases? In fact, this is what you are going to be experimenting this week. You are going to build an erbium doped fiber amplifier where you will look at the gain as a function of pump power as well as a function of signal power. Okay. But what we are asked to figure out is what is the minimum pump power density required to achieve inversion. So, what we have is a rate, right, the rate which is which has a unit of per meter cube per second, right, that is what you have, and you need to actually figure out the pump power density. So, how would you proceed from here? What do you have to multiply this rate with to get power? So, if I were to say what is the pump power density per unit length, what quantity, if you have a rate, what quantity do you have to multiply that to get power? Energy, right, energy multiplied by or energy divided by time is power, right. So, what energy? Energy corresponding to the pump photon, right. So, in this case energy corresponding to the difference between the two energy levels, right, E3 minus E1 multiplied by R, right. So, that would give you the and in this case we are looking at the minimum pump power density. So, we will say E3 minus E1 multiplied by R times minimum. How do you find E3 minus E1? That is the energy corresponding to what? Energy corresponding to pump photon, right. So, it is basically h nu pump. Do we know this energy? Yes, we are told that it corresponds to 980 nanometer photon, right. So, h nu pump you can write it as hc over lambda, where lambda of the pump corresponds to 980 nanometers, right. So, you will find that this is basically 1.24 EV divided by lambda of pump, which is 0.98, lambda of pump expressed in microns, which is 0.98, and then this is in EV. So, what do you do to convert to joules? So, multiply this by 1.602 into 10 power minus 19, and that will be in joules, right. And do we have enough data to calculate R min? Yes, because Na is given, you know, to TSP. So, you can find out R min. So, I can go ahead and write it all out. Okay. So, the pump power density is going to be given by this h nu pump, which is 1.24 divided by 0.98 multiplied by 1.602 into 10 power minus 19 multiplied by your Na, which is 1 into 10 power 24 divided by your 2 times TSP, and TSP is given as 10 milliseconds. So, 2 times 10 power minus 2 seconds. Okay. So, if we do all of that, and mind you, when we calculate this, this comes out as watt per meter cube. Okay. So, this corresponds to a volume, right? It's per unit volume is what you have, but typically pump power density is a cross section. So, you essentially say, okay, if your gain medium is this long, you are pumping from the side and your gain medium is this long, right? That length you multiply over that, right? And then you say, okay, so what you get is in terms of meter square. Okay. So you have a cross section. If we assume, let us say this is 1 meter, this is the length of gain medium, right, then you get a final value in terms of per meter square. So, this would work out to be 10 power 7 watt per meter square. Okay. So, that is 10 megawatt per meter square. That seems like a very large value, right, 10 megawatts. I mean, you look at the room lights here, this is in the order of few milliwatts. Even this bright LED lights that we have here, it's only in the order of few milliwatts, whereas we are talking about megawatts. So, is this even possible? Well, it turns out for the example that we consider, we were talking about erbium dope fiber, right, and the erbium dope fiber is actually a single mode fiber. So, the effective area of the erbium silica fiber is in the order of 100 micron square, right. So, 100 into 10 power minus 12 meter square. So, if you multiply the power density with that area, you get a pump power which is 10 power 7 multiplied by 10 power 100 into 10 power minus 12, which works out to be 1 milliwatt, right. So, although the pump power density seems like a very large value, if you are focusing all that energy onto this tiny core, right, which is what you have to do to make this amplifier, you find that you do not need a lot of power, right. So, in this case you just have 1 milliwatt of power and then you are able to achieve inversion of 0. So, anything more than milliwatt is actually building up your inversion. So, you can start having gain beyond that. So, effective area is the area of your fiber. So, we talked about, sorry, the core and cladding of a single mode fiber, and we said that light is actually confined in the core region primarily, a little bit of that is spilling over the cladding region, right. And we actually said that this corresponds to a certain mode field radius, right, and a certain mode field diameter. So, from that mode field diameter you can calculate the effective area. Okay. So, that is the first part. Any questions about this? Yes. Yeah. So, right, if because it's actually a per meter cube quantity that you get, because our number density is in terms of unit volume, but typically when we talk about pump power density, we talk about power over area, not volume, right. So, I wanted to take that length dependence out, and that is what we did by assuming the length to be 1 meter. Then the question is, what about this guy, how do we calculate the saturation flux density, and for that we need to once again examine our expression for inversion a little more closely. So, the expression for inversion is n equal to n naught divided by 1 plus tau s w I, right. That is what we derived previously, but w I can be written in terms of the flux density multiplied by the transition cross section. So, I can write it as n naught divided by 1 plus tau s phi s multiplied by the transition cross section, let me pick the emission cross section, okay. And then for a given material, tau s is a constant, sigma e is a constant. So, I can choose to write this as n naught divided by 1 plus phi s over phi sat. Phi s is a variable, phi s corresponds to the signal flux density, whereas phi sat is a constant for a given material, right, which depends on the spontaneous lifetime and as well as the emission cross section. So, in this case phi sat is given by 1 over tau s multiplied by sigma e. So, tau s is 2 times TSP. So, that is basically 2 into 10 power minus 2 seconds, and sigma e I think we considered for this example earlier, right. So, sigma e we said is corresponding to 6.5 into 10 power minus 25. So, and mind you, sigma e, when you write it down, it is actually a different number for different wavelengths, okay, because different wavelengths or different frequencies correspond to different transitions, and each transition may have a slightly different transition probability. So, that emission cross section is actually a function of wavelength, but we are picking one particular wavelength and calculating it, and this is what it come out to be. And if you calculate that, it comes out to 7.7 multiplied by 10 power 25 photons per meter square second, right. That is the flux density, the saturation flux density. So, the other way of defining your gain saturation is such that phi s equal to phi sat. When phi s, the signal flux density equals to phi sat, what happens? The inversion goes down by a factor of 2, okay, and that corresponding phi s is what we are calling as the saturation flux density. No, this phi sat corresponds to your saturation of the gain due to the inversion reducing. The inversion is reducing as you have more and more signal photons coming in. So, in this case we looked at the ground state depletion, we looked at pumping very hard, right, such that all your atoms go to the excited state. So, very little atoms, very few atoms on the ground state, and because of that the gain is limited. Okay. Whereas here we are talking about there are so many signal photons coming in which are depopulating the excited state, and as a result of that your inversion is reducing, your gain is decreasing. So, those are two different, one is with respect to signal photons, other is with respect to pump photons. And of course, you can do this exercise. This is actually saturation flux density, right, photon, the saturation flux density. If you want to find the corresponding saturation power P sat, how do you go from flux density to power? What do you have to multiply this by? Area for sure, right, this is the area of cross section, and what else? So, that gives you flux. From flux to power, what do you go, what do you need to use? Energy, right. So, energy over time is power, right. So, energy of what? With respect to the signal transition we are looking at. So, this is the energy corresponding to the signal photon, right. Do you understand that? And if we do the same for, like, the area is 100 micron square in this case, and the signal photon corresponds to, let us say, 15-30 nanometers. If you calculate this, this would work out to be something in the order of milliwatt also. Okay. So, the saturation the saturation power P sat can be picked up, and that also would correspond to about a milliwatt, a few milliwatts. So, that is all we want to talk about as far as 3-level systems are concerned. Okay. And let us have a brief discussion on a slightly different system, and which is very, very important. We will find out why in a few minutes, which corresponds to a 4-level system. Okay. So, what is the structure corresponding to a typical 4-level system? You have once again a ground state, you have an excited state, and then you have one energy level which is relatively close to the excited state, right, relatively close in terms of being within the phonon energy of the glass. Okay. So, because of that you can say that this transition is going to be non-radiative in nature. Okay. So, you have you are pumping, taking an atom from the lower energy level to higher energy level, and then non-radiative relaxation taking it to one level below this, which is very similar to what we had in the 3 level system, except that you have one more energy level over here, okay, and that energy level, let us say, is located such that it's within the phonon energy compared to the ground state. So this is also non-radiative in nature. Okay. So that is a typical 4 level system, and the key thing that we are looking for is transition between these 2 energy levels, which give us gain, which those 2 energy levels are much larger than the thermal energy and also much larger than the phonon energy of the glass. That is very important, because as long as you have the energy levels very close, comparable to the thermal energy or the phonon energy, the non-radiative relaxation is more probable than a radiative relaxation. Okay. So those sort of systems are very difficult to get gain from. So one typical example is, we have been talking about getting gain around near infrared wavelengths, whereas for a lot of sensing applications you need sources in the mid infrared region, 3 microns and above, 3 to 5 microns typically is very interesting. But when you go to 3 to 5 microns, the energy corresponding to that transition, what can you say it will be like when you go to longer wavelengths? Energy will be very small, right, and energy will start approaching the phonon energy of the glass, in which case it is very hard to get these radiative relaxation. So, it is very hard to get gain from a regular silica glass, for transitions at 3 to 5 micron region. Okay. So, what you have to do if you want to get gain for those sort of transitions is to find a glass which has relatively low phonon energy, very low vibrational energy. That essentially means that you have to get to a glass whose molecules are relatively, whose atoms are relatively heavy. If you have heavy atoms, they do not move around very much, the vibration energy is relatively low. Okay. So, in fact, I have done part of my research in making lasers at around 3 micron region, and 3 micron, believe it or not, is what you get when we deal with the terbium. This transition over here, let me see if I can highlight. So, this transition over here actually corresponds to 3 micron radiation, but you do not see that it is actually a non-radiative relaxation as far as silica host is concerned. So, what we had to do in our work to get that as a radiative relaxation is choose a glass host which had very low phonon energy. So, we went to a glass host, it's called Z-bland, it was basically a zirconium based glass, and in that glass the phonon energy was so low that we could get this as a radiative relaxation, and we could demonstrate lasing at 3 microns. At that point, we demonstrated watt level output power from a 3 micron laser, which was a world record. I am talking about almost 20 years ago. But that just giving you an idea of where you get a radiative relaxation versus non-radiative relaxation. If you get non-radiative relaxation, you do not get gain, right. Only for transitions where you can have a high probability of radiative relaxation, that is where you can get gain. Nevertheless, coming back, so if we have a system like this, and we are not talking about some imaginary system, this is actually what you have in neodymium. Okay, neodymium is another rare earth element. Okay, in neodymium you have a structure like this, where this pumping typically happens at a relatively low short wavelengths at 810 nanometers, and this transition corresponds to 1064 nanometer. Okay. So, you get essentially gain at 1064 nanometer. Okay. It is a very popular laser because it is a neodymium which is doped in YAG crystals, yttrium aluminum garnet crystals, can give you very good gain, and you can get watts, tens of hundreds of watts of power from such systems, right. So, they have been very popular, but they are characterized by two things. One is that this if I call this level 0, 1, 2 and 3, okay, and I will say that Ng I will say is the number density in the ground state, N1 is number density in this state, and N2 is number density in this excited state, and N3 is the number density corresponding to the highest energy level there. This is very short lived, meaning the lifetime of that level is very short, okay, whereas this is in the order of milliseconds, relatively long, right. And similarly, this is also short lived. So, can you see what is going to happen when you pump at 810, right? The atom is going to go to level 3, it is going to quickly come down to level 2, typically non-radiatively, and all your population is going to accumulate over here. And what do you have? So, what can you say about the inversion? Inversion is N2 minus N1. What can you say about N1? N1 is typically 0. Why? Because anything that comes to N1 is immediately going to the ground state. So, N1 is practically 0 most of the time, right. So, any single atom that goes to the energy level 2 immediately is available as inversion. So, what can you say about, we talked about and we are moving, we are jumping forward, but that is okay in this case, or maybe I will just go back to this previous thing that we used here. So, this is for a 3-level system. Now, how is this graph going to look for a 4-level system? It's going to look like this. The key point is, with very little pump energy, with very little pump photon, you can immediately get gain. you can immediately get inversion, and through that you can get gain, right. So, that is fairly, sorry, that corresponds to a 4-level system. So, a 4-level system is actually very good from that perspective, that you do not need to have a lot of pump photons to achieve gain from a 4-level system, right. So, in 3 levels you need certain pump power to achieve transparency, meaning your inversion goes to 0, and beyond that only you can get gain, whereas in 4-level systems you can get gain rather easily. But having done that, I can go back here and I can do the same thing that I did before. So, I would say that N A is going to be given by N G plus N 1 plus N 2 plus N 3, but N 3 is going to 0, N 1 is going to 0, because the corresponding energy levels have very short lifetime, right, something the order of tens of microseconds. So, those essentially go to 0, there is very little population there. So, N A is approximately N G plus N 2. So, I can go ahead and write an expression for the rate equation for N 2 and N 1. So, dN 2 over dt is going to be depending upon what? That is going to depend on the rate at which, so N 2 increases as you increase your pump rate, right, and but it will decrease due to spontaneous emission from energy level 2, okay, and then it will increase, or rather let us talk about this first. It can also decrease because of what? What else can happen from energy level 2? Stimulated emission, right, but it will increase because of stimulated absorption, sorry, which depends on N 1. If we assume N 1 to be 0, then yeah, you do not have that term at all, but what we are trying to get an expression for is that inversion. So, at this point we have to keep N 1, because N 2 minus N 1 is what we are trying to get. But of course, like that is what I was saying, I jumped the gun a little bit in saying that you get inversion at very low pumping rates, but nevertheless that is what we will get to at the end. Similarly, dN 1 over dt, if we were writing an expression for that, that would be minus of R 1, that is the radiative relaxation back to the ground state, minus N 1, sorry, R 1 corresponds to or relaxation to any other state, okay. In this case, what we will do is we will say R 1 will go to 0, because there are no other state involved here, but this is actually a generic derivation that is given in your book. But this one will happen, that you could have a rate at which N 1 can get depopulated, but it will benefit from any spontaneous emission from energy level 2 and stimulated emission from energy level 2, and then you have N1 Wi corresponding to stimulated absorption. And like I said, maybe I should not even have written it explicitly. This is going to 0, but because there is no other energy level that it can go to. So, that term we need not even have considered. Okay. So, we do, what do we do next? What did we do in the 3 level system next? What condition did we assume? We are interested in steady state condition. So, we will go ahead and say under steady state conditions, what do we have? dN1 over dt equal to dN2 over dt will be equal to 0, right. So, we assume that, right, and then we go through the same sort of analysis that we did for the previous case, and finally we come up with the expression for the inversion, which we will find is actually of the same form as what we did for the 3 level system, except this N naught and tau s expressions are going to change because of the constraints that we have shown here for the for the 4 level system. So, TSP multiplied by Wi, where Wi multiplied by W, where W corresponds to the pump transition probability, divided by 1 plus TSP W, and similarly for tau s is going to be given by TSP divided by 1 plus TSP W, right, where I should make a note saying that the W corresponds to the pump transition probability. It's W is, is a representation of R. We previously considered R. R is nothing but W multiplied by Ng. Okay. So, I can just write it here, is such that R equals to W multiplied by Ng. Okay. So, yeah, we could have just written it in terms of R as well, just to be consistent with the previous case. But once again, what we are saying is the 4 level system also you have this gain saturation, and to get a relatively simpler peak about what this gain saturation is dependent on, if you take a specific case. So, from here if you take the specific case for weak pumping, so weak pumping is the case where W is far lesser than 1 over TSP. Okay. If you consider that case, then basically in the denominator 1 plus TSPW will become 1, right, under this assumption. So, in this case you say that N naught is going to be multiplied by Na TSP W, right, and that time constant tau s can be approximated as the spontaneous lifetime itself. Okay. So, the important thing to note here is it depends on the transition probability, the pump transition probability, but it does not depend on the number of pump photons, the inversion that you get. And this is what we were saying, that because N1 is typically, N1 is close to 0, is negligible, you do not need a lot of pump photons to achieve inversion. Okay. So, there is not a whole lot of pump power dependence as far as achieving inversion is concerned. Okay. So, that is the advantage of a 4-level system. Now, of course, how we use this advantage, we will actually have to consider the case of a laser before we realize the true impact of this sort of an advantage. So, that will happen, we will discuss that in the next few lectures. But let me stop here, and I also want to mention that I jumped a little bit from the rate equations to the final expression. 2 reasons. One is it's similar to what we have already done for the 3-level system, and also that this is coming directly from Saleh and Tisch. So, if you want to go look at the details, you can refer to our textbook. Okay. So, let me stop there. Thank you.